Hello, everyone. Thank you, Yelena, for the introduction. So let's hope this works. Okay, blockchain. So it's time to run out of the room for you if you hate blockchain, as many people do. And I'm not here to pitch an ICO. I'm not here to tell you how blockchain will revolutionize the economy. It probably won't. I'm just here to talk about the security, the technical aspects. The talk itself is not extremely technical. Probably it's a keynote. It's my first keynote. Typically, a keynote is not too technical, so should be easy to understand by everyone. So I'm sorry there won't be any joke about blockchain because it's too easy to make jokes about blockchain. You can find memes on internet. I could have spent the hour doing jokes, but some of the stuff that I will present will be funnier, hopefully, and it's even funnier when it's real. Okay, so the question is, many people, many non-technical people, they come to me as a security expert and they say, "Hey, JP, this blockchain thing, what do you think? Is it secure?" And I say, I whisper something. So there's no simple response to this question. It's not, there's not one single thing that is a blockchain. There's a variety of different blockchain technologies. And if you take one blockchain ecosystem, let's say Ethereum, there's many components in Ethereum. You have different wallet software, you have the Ethereum internal logic, you have the EVM, you have the network peer-to-peer protocol, you have the smart contract that people run on the blockchain. So it's difficult to say if something is secure or not. But surprisingly, if you look at the history of Bitcoin and of Ethereum, there hasn't been any major security disaster. And then you will say, oh yeah, but the DAO but these one were applications running on Ethereum, not in Ethereum itself. So that's relatively surprising, reassuring that there's no very bad bug in Bitcoin or Ether. So you can also say that maybe these bugs have yet to be found. But from a security perspective, I'm surprised not to have seen more issues in Bitcoin or Ethereum. But what we see now, there are many, many more new blockchain technologies and new protocols are invented every day. There's a lot of code being written. I don't know if you use JavaScript or not. For example, there's a shitload of dependencies, and it's a big mess, and a lot of code that nobody reads, that nobody tries to review. So it's, let's say, an ideal situation for bugs that security people are interested in. So what is a bug in a blockchain application? So there's basically 2 or 3 types of bugs. So what I would call design bugs. So the bugs really in the design, in the functionality as intended by the designers. And in this case, the functionality can be abused by an attacker. For example, the smart contract logic is okay, it's safe, but some people may try to abuse it by writing malicious contracts. And the second category is what I call the software bugs. So when an implementation does not match the specification, when it does not do what it's supposed to do. So typically, the fault here is by the implementer and not the designer of the protocol. Okay. So these bugs are, let's say, in the blockchain itself, again, and not in the applications that people write on top of the blockchain. So now, like I said, there's many components that you can try to attack, so the wallets. So typically, what you're after is stealing people's money, and where's the money in a wallet? So you want to attack the wallet. But you can also try to attack the network itself. And the network is composed of a bunch of servers or of nodes. In the case of Bitcoin, there's many, many of them, thousands, maybe millions. In the case of other protocols, you can have as few as maybe 64 or sometimes 16 nodes. So in this case, the attack surface is much smaller. Okay. So as an attacker, what do we want to do? So like I said, you want to make money. You don't want to work for free. You want to steal people's money. I mean, if you're a black hat, bad guy, or however you call it. What you may do is sometimes you can just, get money, but send money to your own wallet without necessarily stealing people's secret key. So typically, a wallet is defined by its key, its private key, its seed, the secret stuff that allows the owner to sign checks, quite literally. But it may happen that you can exploit a bug where you can, let's say, empty someone's account without knowing their key, without stealing their key. Okay. Another type of attack is when you want just to create money out of the blue and say, oh, okay, here's a new token. And it's like the Robin Hood attack, because you didn't steal nobody's money, you just created money out of nothing. So other types of attack are denial of service. You may want to, like degrade the service. For example, if you short the value of the coin and you expect the value to go down, so then you can do this kind of attack. Or other types of attack that will, let's say, if you create your own blockchain platform and you want to attack a competitor, then you may want to have this, let's say, this kind of PR operation whereby you would find bugs on the other guy's platform and then talk about it to, let's say, degrade their image. Okay, so the official title of this talk, I think it was the top 10 or 10 worst security issues. So I have 10 parts here. It's maybe not the top 10 or the 10 worst bugs in blockchain platforms, but that's the one that I will cover. So maybe 2 or 3 of them are bugs that I personally found. So they may be a bit boring, but hope you like it. Okay, so Bitcoin. So the biggest issue in Bitcoin ever is a very, very stupid bug. So if you program a computer, you have this a variable that can be a 32-bit integer, and on a 32 bits you can only store up to the 32 different values. And if you do 2 to the 32 minus 1 plus 1, then you get 0. There's what we call an integer overflow, or there could be an integer underflow in the other way if you subtract values. So what happened in Bitcoin, it's a CV 2010-5139. It was discussed on the Bitcoin Talk forum by a guy called Satoshi. I don't know if you know him. So what happened in one Bitcoin transaction, so you have a bunch of what we call output values, and each output value has its own, let's say, its own Bitcoin value, or its own value in terms of Satoshi. And the sum of the outputs must equal the sum of the inputs. So, and the output is, let's say, the people who receive the money, to simplify. And what happened in this case is that the sum of the outputs could overflow the size of the integer. I think it was it 32-bit or 64? I don't remember. But what you could do is artificially create a huge amount of money, and when the network would validate that you do own this amount of money, then it will validate the sum of these big amounts. But if you do sum of very big amounts, that you end up with a ridiculously small amount. So the validation was successful because what was validated was the sum. And since the sum had an overflow, then the number was not big, but it was small. So since it was small, it was accepted, and people could create a shitload of Bitcoins. 18446, this fucking huge number. The good thing was that it was detected in just 5 hours, patched in 5 hours, even better. So there was a soft fork, and everything went back to normal. Nobody was harmed, and the code was patched. It was just a few lines of code, what you can see here, and the line in yellow is the most important one. So, as you can see, a very simple bug in terms of software vulnerability, but dramatic consequences. So the second biggest bug, maybe that people know in the blockchain world, is the DAO bug. So I don't know if you heard about it. Yeah. So this is an extremely complicated system. So Ethereum is not just about sending money from one wallet to another wallet. It's about running code, running applications on the blockchain. And these applications are called smart contract. So one specific type of smart contract was called the DAO, Decentralized Autonomous Organization. And this attack was particularly clever because the DAO, they had their own token, so their own money that they created on top of Ethereum money. And the way this attack worked is that when you create an application on Ethereum, it's essentially a smart contract or a set of smart contracts. And the idea of this attack, so I extremely simplify it because it's very non-trivial. But the idea is that you would have the smart contract of the DAO, so the victim, and the attacker would create their own smart contract. And this contract would talk to the victim contract in such a way that the function targeted would call back the attacker's contract, and the attacker's contract would call it again and again. So it's a kind of nested recursive calls, and this behavior is, let's say, is normal. I mean, you can do it technically. It's not a problem that, it's not, let's say, a shortcoming of Ethereum that it allows you to do this. The problem is that you can exploit this behavior to fool the victim smart contract into thinking that it doesn't have the right amount of money. Because a contract, in this case, is also a wallet in the sense that it owns money. So the idea is that the attacker, they would pretend to withdraw money from the account, from the contract. And the contract, it would think that it has less money than it actually has. And what the attacker would do is steal the difference. And the contract will not notice because it's like, oh, I only have 5 whatever token, but in reality it has 10 of these tokens. And the attacker can steal the 5 tokens missing. And the attacker, I mean, he got, I don't know, maybe $150 million worth of tokens with this attack. So again, the fix was extremely simple. It was just one check, one line of code. And you see, just because of this very stupid inequality check, someone could just kill the application. It's just completely scary. And this attack is why many people are like, oh, Ethereum is boring, it's so insecure. Ethereum is not insecure, it's just what people do with it. Okay. And one reason is that smart contract programming is super hard. Now, even simple programming, where you have one single state, is harder. Then if you do multi-threading and concurrency, it's even harder. But if you do concurrency in the smart contract world, it's a complete mess. So now people start learning how to do it, but we have not been educated to think in this way, and there's no, let's say, no good resources to learn how to do it properly. There's a few trainings, but we still have to learn how to do this correctly. So the right thing, you want to, maybe if you do smart contract, it's better to have security audit and ask people who know about this business if your contract is safe. Even the ERC20 contract, which are used a lot, they can be misused. So it's very difficult to write secure smart contract applications. One workaround of some platforms, like Ergo, for example, is that instead of having this full Turing complete set of instructions, they would only allow you to have a limited set of operations. Something a bit more, let's say, more complete than what Bitcoin is doing. So in Bitcoin, you have this notion of scripting, which allows you to implement some logic, but it's not as expressive as Ethereum. Okay. Like this one. Did you know Zerocoin? Do you know Zero Cash, maybe? The thing of Matt Green, Zuko, and other people, Zcash. So initially, Zcash is based on something that was called Zerocoin initially. Did in many changes, and these academic people, they wrote this paper, and they wrote some code, and they put the code online. But they were very well aware that their code was not good, was not mature. So they had put a big disclaimer like, do not use this code in production or use it at your own risk. And of course, people didn't follow the advice and used it in production. And that's what these guys did. So what happened is that they have a kind of, it's a zero knowledge proof that you're allowed to spend some money. And essentially what you want to check is when someone is spending money that they do own this money in the first place. So you're not allowed to spend $1,000 if you only have $100 on your account. And in this system, each coin, they have their unique ID, an identifier of maybe a big integer. And the proof of knowledge, the verification that you're allowed to spend this money involves this identifier. But it was doing it in such a way that the identifier was, let's say, it was viewed as a member of a group of numbers modulo Q, where Q is some, I think was some prime number. Well, this value, the ID was supposed to be smaller than a certain value. But what happened is that they would allow different coins to have different IDs, but when you reduce this IDs modulo Q, you would get the same number. So you could create two different coins, two different accounts that were technically different, but that would be the same from the perspective of the network, to simplify. So what this allowed you to do is to forge money, to spend money several times by creating different coins with different numbers, but that had fundamentally the same identity. For example, if you have the number 10, 100, and 1000, if you reduce them modulo 10, you get the same number, you get 0. So you could create many different coins that had the same value. You could create money for free. And I don't know if people exploited it. I presume that people did, but have no evidence of this. So here, again, the fix was just one line of code, checking that a number was lower than a certain bound. And here maybe the problem was the complexity of cryptography, all this mathematical zero-knowledge stuff that people hate. So it's very powerful, but it's very fragile at the same time. And of course, the lesson is that if people tell you not to use a certain piece of code, maybe they have a reason to do so, and maybe you should listen to them. Okay, that's maybe my favorite one. That's one that I personally discovered one morning when I was bored. It took maybe 2 hours. I started looking at this code, and I'm like, oh shit, they do this. So Lisk is again a smart contract platform that is very different from Ethereum, that uses some kind of JavaScript for smart contract. But here the biggest problem is that the address of an account, so the identifier of an account, is just 64 bits. 64 bits, it might seem big enough, but actually, if you have only 64 bits of entropy, 64 bits of values, what you can do, you can find a collision, which means two different, let's say, two different keys mapping to the same address very efficiently. Because it will cost you only the square root of 2 to the 64, which is 2 to the 32, which is approximately 4 million iterations of whatever you're doing. Okay, so this is mad, this crypto is boring, but long story short, it means that I can create two accounts, two passphrases that are, let's say, distinct, but that correspond to the same account from an outsider perspective. It means that I can create these two accounts, and I get one single address, and you send money to this address, and then any of the two accounts can withdraw the money and steal the money. Okay. Now, what becomes more interesting is that, for example, you have an account, and I know your address, and I want to steal your money. What can I do? I don't know your private key. I cannot break the crypto. I cannot get the private key from the public key because it's hard and crypto is secure. But I can completely bypass the solidity of the crypto. What I can do is look for another key, another public key and private key that will map to the same address as your address. And it's only need approximately to the 64 operations. And you can parallelize it. You can buy a Google Cloud Platform or Amazon EC2, whatever, computing power. And I estimated that if I had spent maybe $50,000 on compute power, I could have made millions in a month. And then if I had spent twice this money, it would be twice faster. So it's bad. It's bad to steal people's money, and it's a bad design from the blockchain perspective. But, okay, that's the details of the attack. There's one way to work around this problem. If you don't want your account to be stolen, then you can just send some money to another account, and then the address will be bound to your private key. But if you just have a cold wallet application, let's say a wallet where you just receive money, you never send money, in this case you will be completely vulnerable. And the response of the blockchain platform was not impressive from my perspective. They just said that, oh, well, we cannot fix it. People should just be careful. And they're right, they cannot fix it because they cannot increase the address size in Lisk. So, yeah, I don't have any interest in Lisk nor other platforms, but from a security perspective, I find it very embarrassing. Okay, back to Ethereum. This one is very funny. So Parity is a group of researchers in the Ethereum community. They are very brilliant people, people who've been in this game for a while, and they have a lot of money, a lot of Ether tokens. And they created a wallet application, and they created smart contracts. and there was a lot of money behind these smart contracts. But one problem is that there was a function called init wallet, and a function that was, let's say, public in the sense that anybody could call this function from the outside without having the secret key associated to this contract. And what happened is that someone just called the function from the smart contract and essentially killed the smart contract. They totally froze the phone. It's like, okay, they completely locked out the wallet. So all the money that was on this wallet is gone forever. I don't know how many million it was, maybe of the order of $50 million, something completely insane. So again, it was super embarrassing for Parity because they were supposed to be, the people who know the best how to code smart contract. And this guy on GitHub, it's famous because I don't know how legit it is, but he said, "Oh, yeah, I accidentally killed it." So you can speculate about the accidentally, but he or she killed it. Okay. IOTA. Is there any IOTA person in the room? I'm just concerned for my personal security. Because every time I tweet about IOTA, even if it's not offensive at all, if it's just a fact, then people from the IOTA community, they would contact me privately and say, "Oh, JP, be careful to what you say." Seriously. So IOTA, it brands itself as the blockchain for IoT platform. There's a variety of reasons because it's not very IoT friendly, but that's another talk. And it doesn't really use a blockchain. It uses something a bit different that they call the tangle. It looks like this. So blockchain is linear. There's one block, another block, another block, and another block, and another block. But IOTA works differently. It's more a graph, connected graph, than a linear blockchain. We never really know why it works, but it seems to work well so far. But one mistake that they did, they created their own crypto, their custom crypto, and it was completely weak. So the single most important thing in a blockchain application, the thing that you want to get right, is the signature, because signature it is what allows you to spend money. And if the signature is broken, then your blockchain is completely broken. And one component of the signature scheme is the hash function. So the hash function is the component that will, let's say, identify the stuff that you sign. And you don't want to have two different transactions that hash to the same value. Because if you have one transaction saying I spent $10 and one saying I spent $10,000, you want to sign the first one, not the second one, obviously. So the problem with IOTA is that the hash function was extremely weak in the sense that you could find collisions. You could find two different messages, two different transactions that map to the same value. So you can tell someone, okay, please sign this transaction. So they would sign, I want to spend 10 coins, but actually you will broadcast the other transaction, spend 10,000 coins. So this was completely ridiculous, but interestingly, not that easy to exploit in practice. So the cryptography people said, "Oh, you're a bunch of idiots because you use weak cryptography and your thing is broken." And IOTA said, "No, you are a bunch of idiots because it's hard to exploit, so it's not broken." So complete lack of communication. So they fixed it, but still it was a big disaster, and IOTA is still suffering from this. So it's good to innovate, it's good to do crazy stuff and to try to be original, but maybe you want to be careful if your system is protecting millions or even billions of dollars worth of tokens. So it's a bit scary, and from my perspective, they should have been more diligent and more careful about this. But surprisingly, the token value didn't suffer too much from this, maybe because they have better marketing than engineering. Okay. Oh, and there's another issue in IOTA. This one is very funny. When there was a special character in the hash value, then suddenly it became weak. So IOTA, they don't do things like normal people. They don't use hexadecimal, for example. They use tries. They don't use bytes. They use tries. They don't use binaries. They use ternary. It's a different world. And when you happen to have this character M in the hash value, then it became insecure because of technical stuff. And the guy who responds is one of the IOTA founders, and he admits the problem. Another very funny one, there was a blockchain platform called Bitgrail. And so they lost a lot of money because of this ridiculous bug. I'll let you read the tweet. So normally, the point of a decentralized cryptocurrency system is that all the, let's say all the nodes or the server that is trusted will verify that you don't spend much money than you have. And in this case, this verification was done on the client, which is complete nonsense from a security perspective, because you cannot trust a client into checking that they have enough money to spend. Okay. This one is on Ethereum, not technically Ethereum itself, but applications or tokens created on top of Ethereum. So, as you may know, many tokens that run on Ethereum, they're based on ERC20 smart contracts. So ERC20 is the de facto standard for creating new tokens. And some people wanted to modify to extend the smart contract with new functionalities. So they wanted to have this function called batch transfer to transfer a same amount of money to a group of addresses. So like I will give you 10 tokens, to 10 tokens, to 10 tokens, 10 tokens. So instead of having many calls to the transfer function, they would have a single call that would take as parameter a list of address, so the address receivers here. But and the value was the same value that you send to each of the receivers. But here the problem was again an integer overflow. So you see the highlighted line amount. So the global amount is just the value that you send to each person multiplied by the number of person. Okay. But the problem is that this number may be huge and may overflow the value of amount. So if the value is very close, let's say, to the size of a UN 256, and you multiply it by the number of people, then the result will overflow the size of the type. So you will end up with a ridiculously small amount. And when you verify on line 259 that the value, that the balance, that the money you own is larger or equal than this amount, then this verification will succeed, because you have maybe more than 0 tokens in your account. But then the value that will actually be sent is not the product, is not CNT times value, it's just the value, which is big. So this allowed people to create again money out of nothing. And there were a bunch of tokens that were affected by this vulnerability. I don't remember the names, but a bunch of shitcoins, I guess. Okay, so again, a very stupid mistake. This would have been spotted in 5 minutes in any security audit by any competent person. So I hope they didn't have any security audit. And yeah, the consequences, as you can read here, attackers can generate an extremely large amount of tokens and send them to their personal wallet. Okay, number 9, we're almost done. Okay, that was quicker than I expected. So Verge is, it's funny. So many blockchain platforms consist more about propaganda / marketing operation, because they have a website, a very colorful, flashy website. They have Telegram account and LinkedIn and Bitcoin talk and you name it. And they have generally a funny animation that explains how this scam is running. And more importantly, they have a white paper. So in the blockchain world, any document, any PDF document is called a fucking white paper, which is nonsense, because a white paper has a precise definition. If you look at Ethereum, they don't have a white paper. They have a yellow paper that explains how it works. And Verge, they wanted to do things even differently. They have a black paper, not a white paper. So it's just a paper with a dark background and white text. Okay. So they're very creative. They do things a bit differently. And they had a very interesting consensus protocol. Oh, and they have the Matterhorn behind, which means that maybe Swiss, maybe it means that they're legit. I don't know what it's supposed to mean. So yeah, the proof of work had a variable rate. So the hardness of validating a transaction was depending on the activity of the network. And more precisely, it was based on a number of blocks confirmed in the last 2 hours. So number of blocks confirmed, it's external input. which is potentially untrusted. And even worse than that, on the last 2 hours, so how do you count the last 2 hours? You use time, you use a clock, maybe use an NTP server. So you need to rely on the time. If you don't have an accurate clock, then your system is fucked. But it was even worse than this. You didn't even have to spoof NTP responses. It was just blindly trusting the timestamp in the blocks received over the network. So what the attacker could do is send completely incorrect timestamps to fool the network and make it believe that there were fewer blocks than there was in reality. And the system would react the following way. It would lower the difficulty. It would make mining easier than it's supposed to be. And if you make mining easier, then it's easier to mine blocks, obviously, and you get the reward. And it's easier to get money just by mining blocks. So instead of doing a computation that would take 5 days, it could just take 5 minutes. Okay. And yeah, more precisely, the decreased difficulty of 99.999999%, which is a lot. And it was worse than this. They did something completely stupid. So instead of having one single proof of work algorithm, they had 5. And so if you had only one proof of work, if you reduce the difficulty, then you reduce the difficulty for everyone, for all the miners, and all the miners will benefit from it. And here the attacker was very smart, because of the 5 possible proof of works, he looked at the one that was the least used by the miners, which was using script. And the attacker only attacked this specific hash function. They only reduced the difficulty for this specific hash, so that fewer miners benefited from the hack. So it was pretty smart. So again, maybe the lessons here is that complexity and bells and whistles might look nice on your white or black paper, but it does not bring necessarily more security to the system. On the contrary, it makes it harder to understand, harder to code, and less secure. So it's from an outsider perspective, if you're not an expert, it might sound more secure to have 5 proof of work instead of only 1. But in this case, it was completely useless. And it's, again, a complete security disaster to make your parameters, your consensus parameter, depending on untrusted input. So many coins, more generally, are vulnerable to time manipulations. But generally, it's more in terms of, let's say, spoofing NTP requests than manipulating simple timestamps. And spoofing NTP requests successfully responses is not as easy as it sounds, because your OS is not completely stupid, and if the time received from the NTP server is too far from the previous time, then it will not accept it. Okay. For the last part, so it's a bug I found a few weeks ago, and yeah, this one was pretty unfortunate, and it made me lose a few days of work. So I want to find a small utility to generate Bitcoin or Ether or other coins addresses and keys. And in the Bitcoin world, typically you have one secret seed, and you generate keys and addresses from this seed using a path as parameter, a path within a tree. So it's a hierarchical key derivation scheme. It's called BIP32, and the way you write the addresses is called BIP44, but we don't care about this. So the way it works, you just give us as an input the seed value, and you get as an output a key or an address. Yeah. And it works like this. So I want to generate an address from a seed of 32 bytes or 256 bits. So I did the following command, BIP32gen -x to tell it that I use hexadecimal, -i entropy to say that I'm using entropy as input, and -o address because I want an address, and m is just the path, the route, just for this example. And I get an address. But if I do the following, I truncate the first 16 bytes, and I do the very same command, and I get the same address, whereas the seed is different. And I was like, oh shit, what's happening here? Now you can guess that the command was just taking the first 16 bytes and not the whole 32 bytes. But if you look at the doc, it's supposed to support different size. So, yeah, the problem is that you had to explicitly pass the size of the seed as a parameter using the -n amount command. And it defaults to 16 bytes. And if you give more than 16 bytes, it will not warn you. And it will just silently fail and take the first 16 bytes. So from a security design perspective, it's a complete disaster. If you design security APIs, this is completely not fail-safe. So I did a pull request and fixed it in its merge. But then it kept crashing. Well, not crashing, but giving the wrong addresses. So it was a different bug. I will not talk about this bug because I didn't find it. So I found out that in certain cases, it will not give the right address, meaning that, for example, you would generate an address and maybe you could receive money on this address, but you will not be able to spend the money because you don't have your seed is not the correct one. And I had lost so many hours with this, so I just stopped using this tool and I started using a more established one, which was a big JavaScript framework, which is called Bitgrail. So this one is a bit more legit. So the previous one, it had only 40 stars on GitHub. So maybe that was my mistake in the first place of using something not super popular. So I started using this guy, which has about 500 stars on GitHub. It's a bit more legit. And it's used by a lot of people, presumably. But the key derivation kept crashing on my machine in certain cases, on my MacBook, but not on the Linux VM I was using. So I won't talk about the details of this, but there was a problem somewhere. And the problem was in SHA-512. So SHA-512, like maybe the single simplest crypto algorithms to implement. You have like a shitload of implementations of SHA-512 that people use every day that are safe, but that one was obviously not safe. So I tried to find out which version they were using. So in these big Node.js applications, typically people have tons of dependencies, hundreds of dependencies, which themselves have dependencies of dependencies, and it's a complete mess. So the function they were using was from this repo, cryptocoin.js/512, and there was a big deprecated on the page, and just 5 stars. They didn't even say what it was deprecated, but still this big Bitcoin project was using it. So I dig into the code, and so that's the issue I had. And the bug was the following. It was a very stupid out-of-bound read, when the function would receive a bunch of bytes of a certain size, and it would parse it as a sequence of big endian words of 4 bytes. And the out-of-bound read happened for the last word because it didn't check that the size of the byte array was a multiple of 4. So if at the end you had just 1 byte left, it would read 3 bytes outside the allocated memory. And it would be detected by my system, it would crash. Okay. But the bad news is that it was unexploitable. Well, I didn't manage to exploit it. Okay. So the lesson here is be careful if you use open source software in production, because if I had used this shit in production, that I would have had very big problems. Very big problems. And the problem is when you use Node.js applications, it's very hard to make a security audit because there's too many dependencies, and sometimes even if you have the latest version of your application, one dependency might be an older version, and you cannot necessarily fix it easily. There are some tools like NSP or npm-dview, but they will not necessarily find everything. Okay. And regarding the first bug on BIP32gen, if you design a crypto API, you should make sure to make it, let's say, fail-safe, or if the user does something wrong, then you should at least have a warning or an error somewhere. Okay. So to conclude this talk, I hope it was not too boring or too technical or too blockchain-y. But maybe the conclusion is that, from my perspective, there are many, many more bugs to be found. The reasons being that the logic of blockchain application is very complex, and not many people are familiar with it. Sometimes unsafe languages like C or C++ are used, which makes the life of bug hunters easier and cooler. Sometimes they also have this notion of time to market. The production is a bit rushed. The code is not necessarily tested enough. In the case of IOTA, there is no, for example, no reference implementation with extensive unit testing. And again, third-party dependencies might fuck you as well if you're not careful. So one recent example is EOS. I don't know if you heard about it. It's huge. It has a lot of groundbreaking features: free rate limited transaction, low overhead Byzantine, fault tolerant finality, time security. It looks super fancy. I think they also have post-quantum. So a lot of features means bigger attack surface for logic bugs and more code, so bigger risk of software bugs. And the cherry on the cake is that it's in C++. And guess what happened? Just literally 1 week after they deployed it, people from Vulkan360 in China, they found an exploitable memory corruption bug, so an RC, a remote code execution bug. And there were a bunch of other bugs found by different people. One where you can read directly from the RAM of the servers. And someone who's a famous bug hunter, Guido Franken, he found, I think, maybe 8 or 12 bugs and got the equivalent of $100,000 to $20,000 in a week in terms of bug bounty. So yeah, EOS was a disaster. So your conclusion, maybe you want to have security audit. I personally do security audits for many companies, and I can tell you that we will not find all the bugs. We do our best. We'll maybe find the low-hanging fruits, but it's far from enough if you want to have a secure SDLC process and have maybe a bug bounty and hire competent people. It's much better at the end of the day than just security audit. But the nice thing is for bug hunters, it's a nice way to make money. Can be in terms of bug bounty, but also in terms of what I call a piñata. If you can just attack a system, if you're a bad guy, you can steal money, and this is your bug bounty. Because not all the blockchain platforms have bug bounty, and even worse, they don't have a security contact, and even worse, they don't even have a fucking email address. I would try to email people, and there is no email contact on their website. You have to go to their fucking Telegram community and find the right guy and explain and make your case. Okay. Oh, but that's the blockchain wallet. It's fun. So thank you very much for listening. If you have any question about blockchain, I will be around the rest of the day. If you have a question about my favorite token or why you should invest, I don't know, maybe you should not invest these days. Or maybe you should because it's super low. And yeah, thank you. It's my website.